Thank you for your introduction. This work is about the DC field induced flat bands in various lattices. So this was done in collaboration with Nana Chang and Walemu Maimaiti. These two fellows were PhD at that time, and also with Alexei and Sergey. This is everyone knows them. So this contains first, I will focus on the case of Brevis lattices, where if you introduce a DC field for a single particle on a Brevis lattice, it can produce Wannier-Stark flatband. Then I will discuss about what will happen in presence of interaction. And finally, I will focus on the NTPT symmetric protection of such Wannier-Stark flatbands. So first, let's consider the Brevis lattice, Brevis lattice. Sorry. So Brevis lattice is defined by a single particle per unit cell, and a dispersion and band means is basically a dispersion relation. And here I will mainly focus on the perfective flat band when the width of this band is exactly 0. Now on a Brevis lattice, if I put a single particle and if I consider tight binding Hamiltonian, I will get only single band. For example, a square lattice, if I consider a square lattice, then I'll have only usually get dispersive bands. And because of the band, because the bandwidth is greater than 0, the particle can transport in such systems. Now I will switch on external DC field, of course uniform, but here I have to care about the directions, which are defined as commensurate directions, which is uh, similar to the demand that the perpendicular direction of the DC field should maintain translation invariance. Then only I can get band structure, and we call this band structure as Wannier-Stark bands. Now there are two kind of band structure possible. One is when along the perpendicular direction of the DC field, the lattice sites are connected by hopping, and for other case, there is no allowed hopping. And this, the second case is actually infinitely many numbers. So there are many possibility for this case, but here are few possibility for example, for a square lattice, I have two such directions. So I will mainly focus on the second case. For the second case, when we don't allow any hopping along the perpendicular to the field, all bands are turns flat. And flat means there is no zero group velocity and the particle cannot transport in such system. We analyze the special properties of such eigenstate of such flat bands, and they are non-compact and super exponentially localized. If you look at the figure, this is the modulus of the eigenfunction amplitude as a function of position in log linear scale. And this implies this is the distribution is not exponential. It's faster than exponential. For reference, you can for the details you can look at this reference. And then I will turn on two particle on such system, and I will introduce some interaction, contact interaction between these two particles, where H1 and H2 are the single particle tight binding Hamiltonian in presence of DC field. Of course, this is the case for the second case, which will produce exactly flat bands. And what happens, this interaction will induce some kind of dispersion in the flat band case, and it will allow only pair particle motion perpendicular to the field. So all other kind of motions are suppressed still. And we analyze for the case when this interaction strength is very, very small compared to the hopping strength, and the field strength is very, very large. Then we found that group velocity along the perpendicular to the field is actually varies linearly with this V, and acts as power law of with the field potential field strength. And this power nu actually depends on the field directions. For numerical study, I choose this parameter value V equal to 0.1 and F is 9. And then I took a finite square lattice and I started from a two particle, which is sit around the center initially. And then DC field is along the diagonal of the square lattice. What I found, this is the final probability distribution in position space. The particle only distributed along the perpendicular to the field. And if I observe the time evolution of such system, I found that for this case, I calculated four different kind of coordinates. One is center of mass coordinate along the field. Another is center of mass coordinate along the perpendicular to the field, and other two are relative coordinates along the perpendicular to the field and along the field. And I calculate the RMS or actually square root of the second moment for each of them case. And what I found, only the center of mass coordinate, which is perpendicular to the field, evolve ballistically. All other coordinates actually turn saturated with very nearly zero value. So this implies that our theory about this claim that these two particles move jointly perpendicular to the field is valid. And then I will, so far I discussed only the Brevis lattice case. Now I will ask whether there is it's possibility to get Wannier-Stark flatband on non-Brevis lattice, non-Brevis lattices. So non-Brevis lattice are actually defined by if we have more than one lattice sites per unit cell. And the answer is given by if I consider a some kind of symmetry, it's possible. So what we consider? We consider jointly two symmetry. One is point reflection, and other is complex conjugation operation. If we consider this symmetry, and that we define this as NTPT symmetry. And so that is basically under the symmetry operation, the Hamiltonian changes its sign. So this is different from the unitary symmetry. Chiral symmetry is one of the example, because of this presence of T, this complex conjugation operations, this is an anti-unitary symmetry. And because of this symmetry, we always get pairwise eigenvalue for each momentum. For each E, we have minus E. And in such system, if we have odd number of sublattices per unit cell, that automatically implies for each E, I have that implies we have a single E for which this eigenvalue is just opposite to itself. That means this is zero for all K. So that implies a existence of a flat band at exactly at E equal to zero. Now we check that this NTPT symmetry persists in presence of DC field, and that implies that flat band exists within each Wannier-Stark flatband structure. To demonstrate that, we consider 3D generalization of Kagome lattice with NTPT symmetry, and this is formed by stacking 2D Kagome planes vertically on top of each other. So this is Kagome lattice. So we stack this vertically, and the left figure is for the band structure without DC field, and it contains E equal to, so of course this is now a three-dimensional momentum space, which we cannot show, but we fix one of the momentum at some value, like K3 equal to pi by 7, and we show that E band structure as a function of two other reciprocal momentum. And we found that at exactly equal to 0, we have a flat band. Now we turn on the DC field, and we found that still this flat band persists within each irreducible structure of the Wannier-Stark bands, like E equal to 0 and equal to around 2 to minus 2. So actually Wannier-Stark bands, it's in two-dimensional momentum space, and the number of band structure is infinite, but here we showed only 3 of them. And each irreducible structure contains a single flat band. So what as a conclusion, what I showed that if we use uniform commensurate DC field, that can induce a Wannier-Stark flatband on Brevis lattices, and this eigenstate of this flatband are super exponentially localized. Introducing interaction, a two-particle interaction on such system can induce particle motion, but only along the perpendicular to the field. Now, in presence of antiparity symmetry and odd number of sublattices, a non-Brevis lattice can hold a flat band. In presence of DC field, the same antiparity symmetry can protect Wannier-Stark flatbands in such systems. And this is for the details. You can look at these two references. One of them is published and one of them is still in archive. Thank you for your attention.
So thank you for this interesting talk. Where do I clap here? Okay. So there are questions I see. So Dario has a question.
Yeah, thanks. Actually, probably two. Let's say one is how can I understand, or let's say, is there any, how can I say, simple logical explanation why a DC field in the Brevis lattice induce a flatband?
Well, so there are two cases. When for the second case, if you look at that, if you introduce DC field, we are not allowing any hopping along the perpendicular to the field.
Right.
So that means there is no equipotential hopping, equipotential surface where particle transport is possible.
I see.
Right.
I see. Okay. Okay. So I see. Okay.
Yeah.
And
yeah, but
the other
let me add to this. I'm sorry, but Arindam, I don't agree. I mean, this is not, you can go around, you can go zigzag, and you do two hops and you are back on a site which has the same energy. So why is there a flat band? I think that doesn't answer the question, right?
This is, I mean,
okay.
I mean, why are you finally not running away and localizing in some whatever way?
This is the final answer. If I can tell, this is kind of interference is happening in presence of DC field. If we don't allow the hopping partner.
Yes, localization is interference. This is true, but why does it happen? That's a very good question.
Yes.
I think we don't have a simple answer to that simple question.
From the basic observation, it's like if we don't allow the direct hopping along this on the equipotential surfaces, that produces flat band.
Yeah, but that's an observation.
Yeah, that's observation. That's probably that is
the
related to
question
interference.
Was exactly if you have, let's say, a first, I mean, a simple argument to understand this a priori before observing it or not. It looks not really, right? I mean, it looks something that is still, let's say, under understanding, under investigation somehow, right?
Yeah, you can tell that. So this is the first observation is that if we don't allow any equipotential hopping, that produces flat band. But there is, and the flat band means some kind of interference is happening. But in between, we don't understand properly what is happening.
Okay, and the other question is, when you show that somehow you add, let's say, interaction and you put two particles and you show that kind of motion. I mean, if you put more particles but still the interaction is just two particles, the situation changes a lot or not really?
No, I think that will be similar, because in presence of DC field anyway, along the field direction, because of energy difference, you cannot propagate much. And you'll have only allowed only along the perpendicular direction.
I see. Okay. Okay, good. Thanks.
Okay, thank you.
Jong-Yan has a question.
Thank you. That's a very interesting talk. So another question about this anti-PT symmetry.
Okay.
Actually, I've never heard about it. Is it the physical symmetry?
Sorry?
Is it a physical symmetry? Usually, if you have an inversion symmetry with a complex conjugation, actually you usually have a plus sign. Actually, here you have an anti-symmetry, right? Usually, the PT is the symmetry of such a system. Why do you have a minus there? Why?
No, that why do you want to? So we consider this kind of, so if you under special reflection and time reversal operation, this Hamiltonian changes its sign.
I mean, why?
Yeah, why? That's my question too.
Why? I mean, well, we consider this kind of Hamiltonian,
No,
which obeys this.
No, that's not the physical symmetry. Usually, you know, even in material, there are many systems which have inverted symmetry with for example, spinless time reversal symmetry. In that case, you have a plus sign. That's very common, but you have a minus here. So why such a minus happen here? Actually?
I mean, you would have.
Can I add to that? So, Bomjung, if you take the chiral symmetry, you have chiral protection of flatbands. It's the same thing, except that this crocodile, which is here called tau times p, is then something different, and it is actually a unitary operator, and still it is an anti-symmetry, so it changes the sign of the Hamiltonian in the same way as it does it here. So basically you say basically you can look for such symmetry. You can say, let me assume that I find a Hamiltonian which has such a symmetry. Okay, then that's how it looks like, and then you look for Hamiltonians which do the job.
But that's why I'm asking, is it physical or not, actually?
It's physical. I mean, what do you mean by physical? Whether there are examples where you can...
Yeah. For example, if you have, the lattice structure shown in the screen, you have inversion and also this spinless, for example, time reversal symmetry. And usually the combined symmetry is a symmetry, not anti-symmetry usually.
No, if you do this reflection, if you do this reflection and in space and the time reversal, then it's an anti-symmetry, as it happens to be for the.
Yeah. Okay, so I think about it, but to me, it's not very natural. Okay, thank you.
Not the usual, but you can construct such Hamiltonian. I mean, think about some kind of non-abelian symmetry, right? This is because this P, you can write it as a unitary operator.
I think it's different actually.
Yeah,
I don't understand properly your concern.
But usually,
I think of the.
Yeah, can I ask a question?
Magnetic field, I would say. Somebody has a question, but raise your hand because I don't see who.
I have a question, Barbara. Isn't it this problem like the Stark effect with the linear electric field? And don't you have problems if you solve it with periodic boundary conditions?
This can also be true for if you use periodic boundary condition, but you have to maintain this reversal. So there should be for each R a lattice vector. I should have another lattice vector which are just reflect minus of that.
You don't mean that the lattice has some inversion symmetry?
Yes, lattice have some inversion symmetry. Others, so if you don't consider the DC field, we don't probably need that, but we are some kind of you can construct some kind of reflection by some unitary operator. But the the DC field is exactly excess potential, which is linearly act on E times R, right?
Yeah.
And the reflection, the reverse of this sign exactly needs, if we consider the so we have to consider this reflection on the lattice to reverse its sign of the DC.
So my question basically is, what happens if you consider an infinite lattice? Do you have infinite potential?
Infinite potential, infinite percent, even strength.
I mean, if you consider a very, very big lattice.
That is not a problem. This is true for any magnitude. I mean, it can be very small or very large. It will not change. It is true for any large, any kind of potential. But it has to be linear on the lattice position.
Of course, yeah.
Okay. So Christian Bonius has a question.
Right. So my question was actually exactly the same as the first one regarding the DC field, and then continuing that shortly. to explain this destructive interference, which I suppose is a condition for having this all bands flat, could you say that in the hopping elements of the DC field Hamiltonian, one gets effectively some kind of pi flux magnetic field, which would cause effectively some sort of Landau levels or something like that?
No,
So
I
you get
don't think
signs on the hopping element phases.
No, I don't think some kind of. So if you
right.
So if you consider all hopping is just exactly same, that means zero magnetic flux. Still, you support this all band flat.
All right. And then, so another short question.
It does not depend on time.
Sorry?
I say that if the electric field doesn't depend on time, you would not have a magnetic field.
No, not a magnetic field. I mean, effectively, that you get a Hamiltonian with hopping elements with signs on them, which would effectively could be interpreted as pilot phases of
Yes,
pi
I
flux.
understand, because we checked that without, if you consider all hopping are real, exactly real and same, still you can get this kind of all band.
And do you get this for any DC field value or
yes,
strength?
any value, any value.
Any infinitesimal value?
Any infinitesimal value.
Just makes the bands flat automatically.
Yes, you have only have to consider the case where you don't allow equipotential hopping in the Hamiltonian.
Right. Okay, it's very interesting. I will look into the paper. Thanks.
Because Dilip Nandi has a question.
Yeah, I have just an extension to the Dario question. For example, like, so it is independent upon statistics. I mean, what kind of particle you have? Is it boson or fermions?
We just consider single particles. So for this,
no, in case of interacting.
Oh, in case of interaction, okay, we consider distinguishable particle, but this is valid for bosons also, because this is only happen for contact interaction and spinless case. So when these two particles are at the same site, only they can interact. So for fermion, this is not valid.
But for spinless fermion or spin polarized fermion, it could be valid, right?
Spin polar we did not consider here. We cannot tell. Probably this will be valid for spin. So then we have to modify the interaction accordingly. But here there is no spins.
I see. Okay. Thanks.
Okay. So then Alexei also has a question.
More of a comment to the question by Christian. I'm not sure how easy, I mean, I think in this problems, the usual intuition with flatbands doesn't really work. I mean, to begin with, these flatbands do not have compact localized states. So destructive interference definitely does happen, but in a much more complicated way, I think. So it's not like you have some simple conditions that ensure that the amplitudes do not spread. You get super exponential localization basically instead of just the compact one. Yeah, that was all I wanted to comment.
Okay, so there don't seem to be more questions. So let's thank Arindam again for his interesting talk.